Last time we talked about geometric trigonometry. In this video, we're going out of the real world. We're going to complex numbers. Starting off with the basics. I is the square root of -1. I squared is -1. I cubed, -I. I to the fourth, 1. And it cycles every 4. I squared, I cubed, I fourth. These are just I, -1, -I, and 1. And this keeps cycling. So let's say you wanted to find I to the 57. It would be equal to I to the 1 because 57 and 1 differ by a multiple of 4. Okay, adding complex numbers. A plus bi plus c plus di is just a plus c plus b plus di. Subtracting, pretty similar. Multiplying, well, we just do each term AC, ADI, BCI, and finally here we have negative BD because I squared is -1. Yeah, so we have a complex number is the real part and the imaginary part. The real part is this. The imaginary part is this. Conjugate, you just make this plus BI a minus BI. And yeah, there's also the complex plane where you can graph a complex number on the complex plane. For example, this is 4 plus 3i. Also, the magnitude of a complex number is denoted as the absolute value of c, although it's not absolute value, it's magnitude. So it's kind of like the absolute value symbol. And it represents this distance. Naturally, it's just Pythagorean theorem or standard distance formula. This is what you can see over here. Okay, now multiplying complex numbers. A plus bi times a minus bi is this. A squared, and then a minus bi, and then this is abi, this is minus abi, they cancel. And then this times this is b squared. We end up with this. And it's kind of similar to difference of squares, which is this. Okay, now for a complex number, this is basically the same as the previous property, but this is so useful. You have no idea how useful this is. And this is a minor typo here. That should be. Z times its conjugate equals the magnitude of z squared. And notice how this is literally this thingy above, because this is magnitude of z squared, that squared. This is so useful. In fact, let's see an application of it right here. Let n be the number of complex numbers z with the property that magnitude of z is 1. And this is a real number. Basically, find n. Find the number of complex numbers that satisfy this property. And then we can easily do this. First thing to notice here. Magnitude of z is 1. So it lies on the unit circle in the complex plane. Okay, now what else do we know about this? Z to the 6 minus z to the 5, or sorry, z to the 6 factorial minus z to the 5 factorial being a real number. And now we're actually going to utilize our property straight away. Notice that because this is also true, just by squaring, and from this, we get that z times z conjugate is 1 as well. So that's pretty cool, isn't it? And here's another thing about complex numbers, which is kind of obvious, but still so useful. Let's say you have a complex number z. So first of all, oftentimes if you're dealing with complex numbers, it's a good idea just to write it as a plus bi or something plus something else I. It doesn't matter what variables you. Because then you can deal with the real part and imaginary part separately. So in this case, you could be like, okay, let this be a plus b and something like that. And then you can try and solve from there. And actually, there's a solution with this using polar coordinates, roots of unity, where you let this be like cis of theta, which we'll talk about in the next video. And you also let this be cis of theta. And then after that, you use some roots of unity stuff to find out when these things are equal. That's one solution. But take a look here. When you have a complex number z, its conjugate is a minus bi. But if a number is a real number, then both of these terms are 0. So if z is real, z equals z conjugate. Now similarly, if z is purely imaginary, so there's no real part, then we have this. Now, this is sometimes a good condition you can check for when these things actually happen. And let's take a look at this being utilized in this problem. Okay, so for this to be a real number, what do we need? We need this has to be equal to its conjugate. Now, there's some really cool properties about conjugates. This thingy's conjugate. There's some really cool properties about conjugates, and that is if you have a conjugate and you add it, it's going to be equal to a plus b's conjugate. Similarly, if you have two numbers and you multiply them, we're going to have this. And of course, this is just derived from the previous one. This is also true. And this is just derived from this. These are some really useful properties about conjugates. They're not that difficult to derive. You can do that on your own if you would like. But using them, we get that this z conjugate to the power of 6 factorial minus z conjugate to the power of 5 factorial has to equal to the thing above. But then, aha, z conjugate is just 1 over z by this. So now from here, we just say, okay, z to the 6 factorial minus z to the 5 factorial equals 1 over z to the 6 factorial minus 1 over z to the 5 factorial. Now, multiply by z to the 6 to the whole equation, z to the 6 factorial. You get this. Equals 1 minus z to the, what would it be? It would be 6 factorial minus 5 factorial. And take a look. This has a degree of 1440. 1440 is the degree of this polynomial. But you know, fundamental theorem of algebra, if you have a polynomial, counting multiplicity, there's going to be 1440 solutions. 1440 solutions because of fundamental theorem of algebra, right? It's complex number solutions. So that is our answer for this problem, but of course, remainder when divided by 1,000. So we can just remove this one. And yeah, and that's our answer for this problem. 440. Okay, but how do we know that there aren't any double roots for this equation? We have to make sure that all the roots are really distinct. Let's try and figure out how we can maybe do that, or if it's even true. Z to the 1440 minus z to the power of 840 plus 2z to the power of 840. And then what else is there? We also have a minus 1 term at the end. Those are all of our terms of our equation. And can we maybe factor this, perhaps? Is this factorable? Oh, sorry. Actually, this should be minus z to the 840 plus z to the 600. I did not realize that these things. So, and then this minus 1. Okay, so now how can we factor this? This is pretty easy to factor. Just z to the 840 plus 1 times z to the 600 minus 1. How will we do that? Well, you just group these together, and then you realize that, okay, this is just the same thing scaled up by z to the 840. Okay, so the question is, now take a look. All of these roots and this, all of these roots. So if z to the 600 is 1, and z to the 840 is minus 1, is that even possible? We'll take a look. If this is the case, then we also have z to the 240 is minus 1 by just dividing. But then we would have z to the 480 is 1 by squaring. And then we divide this equation by this equation. We get z to the 120 is 1. But then that z to the 240 is 1. So that's a contradiction. So if there was a value of z that satisfied both of these equations, we would be at a contradiction. So therefore, there's no double roots. All of our roots are distinct, and we're good. This is the correct answer. Okay, now just to summarize really quickly, the key steps here. These conjugate rules, super duper important. Don't want to forget them. Second, this identity. Literally, it's so useful. And then we put it in, we got a quadratic, we just solved that quadratic, and we're like, okay, nothing common, we're good. And that's it, that's their answer. Okay, now we're finally moving on. Complex numbers satisfy the system. Find the smallest possible value of this. We're looking for ZW here. How can we get ZW from the equations we're given? We got a Z here, we got a W here. We should maybe multiply them. That will give us this term. Let's do that. ZW, right? Blue term times blue term. This times this is 12i. And then this times this is 20i. And then finally, we have this times this is minus 240. Because I squared is negative 1 over WZ. And this is all equal to minus 30 plus 46i. Let's subtract 32i from both sides. Naturally, we want to do that. And this is actually really cool because now we've basically got a one variable equation that's purely in terms of ZW. There's no other terms. There's no like Z's and W's individually. It's just one thing. Because everything else that just had one term just canceled out pretty nicely. So what we're going to now do is say y equals ZW. Why? So we can just deal with one variable. And really now this is just y squared. Magnitude of y squared. So y minus 240 over y minus 30 plus 14i. Okay, now what? Multiply by y to the whole equation. Y squared minus 240 equals minus 30 plus 14i times y. And then y squared plus 14i minus 30 minus 240 is 0. And now we just use quadratic formula. So 30 minus 14i plus or minus the square root of that thingy squared plus and then 960. Just applying the quadratic formula here. All of this over 2. Let's divide out by 2 to everything. We get 15 minus 7i plus or minus square root of 15 minus 7i squared, right? Because square root of squared will end up, if we divide by 2 here, then it will end up dividing by 2 to the thing that we're square rooting as well. And then now because we're inside the square root, we divide by 4. So essentially, to divide by 2 to the whole numerator, this part we just divide by 2, and we divide by 4 inside the square root. But that's also effectively dividing by 2 inside this term. And now it's just a little bit of... There's actually one tricky step left still. Never mind. So let's take a look here. Got this stuff. What is that? And what is that stuff inside? So 15 minus 7i squared equals 225. And then that would be minus 49. And then minus 210i. And that's just 176 minus 210i. Now we add 240, we get 416. 416 minus 210i. Okay, so now the question is, what is the square root of 416 minus 210i? So let's just say natural trick is when you don't know what it is, let's just let it be a plus bi. Now we square both sides. We get 416 minus 210i equals a squared, and then that would be minus b squared plus 2abi. Okay, so now we just say a squared minus b squared is 416, and ab is negative 105. So what should we do from here? Now, you could try and do is guess and check some values. I mean, it is possible to mathematically solve this, but that's going to be a little bit annoying. So maybe if you can try and guess and check some integer values, that would just be a little bit nicer. So what are two values that product have 105? Well, that could be 21 and 5. It could be 7 and 15. But the thing is, notice that one of the values has to be at least, like, look at this, 416, right? 20 squared is 400. So A has to be at least 21. The larger of these, at least one of these has to be 21 or more. So that really leaves us with, very few possibilities. 21 and 5 and negative 5. We have 35 and 3, negative 3. And then obviously we can flip the negative. We can put it here and here. So now we can just try them both. 35 negative 3, that's going to be 35 squared minus 9, which is like 1,216. Way too big. Now what about this? 21 squared minus 5 squared. 21 squared minus 5 squared. That would be equal to, or 21 squared is 441. And then minus 5 squared is 25. So we get 416. So yeah, that works. That's pretty cool. So 21, negative 5, or negative 5, 21. Both will work. And that just gives us this plus or minus 21 minus 5i. And that really gives us two possibilities. Either 36 minus 12i, that's the first possibility. And the second possibility is going to be, it's just going to be, you subtract it, so it's going to be negative 6 and then minus 2i. These are the two possible values. So now the question is, which one has a smaller magnitude, right? Because we're looking for a minimum value of this. This is a magnitude of root 40. This has a magnitude of root something way bigger. We don't even care. So clearly, this is going to be the one. It's going to have the smallest possible value of or magnitude ZW. So our answer is just square root of 40 squared, 40. It's a pretty neat problem, where the key idea really is multiply the equations to get everything in terms of ZW, because then we can just directly solve. And then after that, we got this. You don't get scared by, oh, we got i's in our quadratic formula, because we can just do this at the end. And then write a simple equation, and then you can just probably be like, okay, this. Oh, integers work. Now you might be like, what if these solutions were not integers? Then how would you possibly solve this? And then this problem would be quite a bit harder, because you would have to solve it algebraically. You could not just do it. But one way you could do that, I'll just suggest it in case you encounter this. Because in this case, it was nicely integers. You could just be like, okay, b equals minus 105 divided by a. Then you can plug this in, and then you would get a quadratic in terms of a squared. You know how we do the standard y equals x squared trick when you have something like this? So you do that trick, and yeah, you get the value that you were looking for. That's about it for this problem. On to the next one. There's a complex number z with imaginary part 164 and positive integer n. So complex number 164. We know it's going to be of the form a plus 164I. Oftentimes it's a good idea just write it in terms of the real and imaginary parts, a plus bi. And another strategy, generally with complex numbers, there's two things you can do. Either write it as a plus bi or write it in polar form. And in this video, most of them will deal with a plus bi. And sometimes you can even just deal with the complex numbers directly, just straight up z. And then in that case, maybe you can use identities like this one that we use here. So yeah, like 3 strategies in general. Number 1, just use z, or just use one variable for the whole complex number. And in that case, this identity is very, very useful. The second strategy is use a plus bi as your complex number. And then you can just write an equation separately for the real and imaginary part. The third strategy is polar form. Roots of unity. And we'll talk about this stuff later in the next video. So you can check the next video for that. In this problem, we are using the second strategy, a plus 164I. All of this divided by a plus n plus 164I equals 4I. And now we can just write it, a plus 164I equals, that would be negative 656, and then plus 4a plus 4n I. Okay, and now we have that we basically have an equation. Now what we can do is we can compare the real parts, which have to be equal, and the imaginary parts, which also have to be equal. And this problem is really not that bad from here, because a has to be negative 656. The real parts have to match. The imaginary parts also have to match. And now this is pretty simple, isn't it? We can just solve for n. So we get 164 plus 4 times 656 is 4n. And we just divide by 4, we get 41 plus 656, 697 is our answer. It's not a very difficult problem once you realize that, okay, just write it in this form. Okay, now polar form. In the next video, you can click on it right there. See you next